Okay. All right, Chris, then let's get started. Okay, John just confirmed, so let's get started. So, Chris, when you click run, why don't you just let us know, and we'll see things start moving.
Just launch it.
Great. All right, we have initializing, and we're running. Let's see, once the markets start trading, and teams, just confirm that you're seeing the same things on your screen.
Greenlytics, we can see it.
Perfect. Takes a little while for everything to get started, and then once we see the first market slots, great, looks like we have trading. I see some VUCA trades. Okay, Greenlytics is trading. VUCA, you traded, you missed one market slot for some reason. We can see if that's if I'm going. Oli, I don't see any trades from you. Are you were showing connected?
Yeah, for some reason we just started trading now.
Okay. All right, good to know. We'll see. Hopefully that shows up in the next slot here. Yeah, perfect. Okay. So we'll do a quick tour through the results so everybody sees what's happening at a very high level. So the way that this works is we're running through the simulation just as we described earlier. We have the grid zip code broken into 2 different communities, and then each of these has their individual devices under them. And what's happening is the load and the PV and the battery come with a template trading strategy, and each of the teams have now connected and overridden the trading strategy through the API. So instead of there being just the linear strategy of trying to buy low and sell high, that is template in the D3A, we're now using information from the market, things like the historical market stats and the total energy traded in the past and the energy requirements of the devices to predict the price and make decisions on the price. This is less complex than it would be in practice because we're giving the team specifically how much energy they need to trade. In the future, in the Canary network, in our deployments, teams will and data scientists will have to predict things like the amount of energy that's going to be used, the total supply and demand in the market going forward. So exciting stuff. In the results page here, we see at the very high grid level some different metrics for the grid. We see the energy bills and how energy is traded. This is at the grid level just going to be the market maker because that's all that's there. Much more interesting is the trading between the communities and the zip code. So what's going between community A and B. And we will pull out some specific results to show you examples of, but I'm just kind of walking you through. So we'll go more in detail into inside community A, what's happening. So at the very top here, you have the progression of the simulation. So it's 2% through the entire simulation, and we're running for 7 days. The self-sufficiency and self-consumption of the community will show up soon once we have more data. You have the total amount of energy traded. Right now it's just loads. Once you have more, once the PV starts generating in the middle of the day, you'll have a lot more going on. So we kind of have a slow ramp up to that. And that's when the batteries can also start making intelligent decisions. And right now, everything is being bought from the market maker because we don't have any PV generation. But we have a couple variables in there, like a CHP, combined heat and power, that generate at random points during the day. And we'll see if the agents can adapt, which is cool.
Colin, what is the speed of the simulation now?
So the speed, we have it at a slight slowdown factor. So we have about 1 hour and 40 minutes left of the simulation.
So an hour 40. So we get 7 days through in an hour and 40 minutes. Yeah.
Yeah. and we actually had to slow it down because the simulation was running too fast for the agents to be able to make decisions. So we've slowed it down to give them a little bit of time. In a real world, this would be running, you'd have 15 minutes, whereas now you have probably about a second to make a decision.
Yeah.
All right, so we should see the prices start to drop here soon when trading starts occurring. And also kind of a cool feature here is the bid offer and trade graph. So you see that how different devices are trading in different strategies. So green storage, for example, here has a very high strategy, it looks like, to try and bid right under the market maker price and try and get people to sell to them instead of the market maker. We'll see if that works. And once the PV starts trading, we'll have more interesting results here. So now that we have that going, let's reveal the challenge question, and then we'll bring you back to the results as interesting things happen. All right, so big reveal. And the way this works is you, with your team, can come up with an answer to this challenge question, and during the debrief, we'll have you all just give a quick, very informal presentation where all the teams will be more collaborating than competing to talk through the challenge question. So starting pretty easy with challenge question 1. How did you approach designing your agent? What information did you use as inputs, and what are your outputs? What other information could be provided for more accurate, robust predictions when you're predicting other factors such as energy use along with price? So put something together. You can use this free space over here if you want to do it publicly, which I'd encourage, and just kind of share information between teams. We can also have a conversation about pieces of that on Slack. Really, really cool here. So I'm looking down at the Greenlytics page, and we're seeing how the different bids are happening, or how the different trades are happening with their PV. So now that the PV is generating, we're having a lot more variation in energy prices because there's more of a supply-demand market. So you see slowly as the amount of energy goes up, this price seems to be dropping. And same with the storage. They seem to be buying slightly here. So let's see what they do with their energy. And we can go down to their actual house market and see the energy price kind of slowly dropping here, which is great. And then we can go into their bid offer trade curve and see how different things are occurring, so that we can go in and see how all the purple dots are bids and all the green dots are offers, and then these blue dots are trades. So tons of information because we have so many different agents trading. The download file for this is something like 17 gigabytes. But we have it all presented here in a way that should let you examine it a little bit. If there's anything on the results page that you think would be interesting to add or was a little bit tough to figure out, please add it here to the feedback and ideas. And also copy paste any sort of images to the interesting results as well. So I'll shut up for a little bit and let the teams think through the challenge question, and we'll interrupt the stream whenever we come up with some interesting outcomes.
Maybe it's worth to mention, Colin, that all the teams can actually also see the bid and ask, so the bid matching graph, right?
Yeah, they can all see the bid matching graph. We don't expect you to scrape that to try and figure out the other team's strategies, but it's a way to kind of confirm that your strategy is working well. So one of the challenge questions will involve you kind of analyzing how you did. This is a heads up. So start thinking through how you might do that, how you might be able to share that. So here's an interesting one with OLI here.
Yeah, so in a classical...
Sorry, go ahead.
Yes. Yeah, I just wanted to add, so in the clearing mechanism that in the D3 we have 3 clearing mechanisms, and for this specific simulation we have chosen a double Dutch auction where both sides are kind of bidding inside, asks and bid. and normally this auction would be blind, meaning they wouldn't see the other side. Now, for the simulation, we decided to open the bidding, let's say the clearing graph, just for everyone to see, because it helps a lot in debugging. But in reality, this wouldn't be visible. And I mean, in reality, teams would also have much more data. You know, would have a much bigger past to train your agents. But then also additionally, in reality, you wouldn't get a perfect prediction of the demand and supply side on the energy side. So you would have additional difficulties to predict what the users in the home are doing, so demand and supply side. So if we look at the markets right now, I mean, at the energy markets, we recently saw Tesla pushing their auto bidder product. And this goes directly into this direction. So where Tesla as a vendor is pushing, is adding a trading strategy or a trading agent to market the assets they are selling to their clients. And so essentially what the teams are doing here right now is exactly what the auto bidder does, with the difference that the teams here in this first stage are only trying to predict the best price according to the curve they received for demand and supply. So they got a perfect prediction for demand and supply. At a later stage, when we, you know, as we progress in this hackathon, we also want to add these new variables to the teams, where they also have to forecast demand, supply, probably weather as well, and also the right prices, which is exactly as the auto bidder of Tesla is working.
So here's an interesting result here, and Sarah, help me think this through if I'm seeing this the wrong way. But the blue line here is at the very top. That is the baseline peak imports. So we ran a baseline scenario that showed what would happen if we just had the template strategies and what was going on there. With the intelligent strategies, it looks like currently our largest peaks are much smaller than the baseline. But we definitely need more data to see if that's happening correctly.
Yeah, I think we'd expect the peaks probably to happen either times where there's maximum PV that's being sold back to the market maker, or during times where maximum energy is being consumed. So I would expect the max PV to happen in the middle of the day, and then maybe the max load happening more in the early evening. But let's see what results we get.
Great.
I made one other observation in Miro, and I just noticed, at least in the beginning of the day, this is at 2:30, there's Greenlytics, they matched with the market maker right away. There's no PV being generated during this time, so I think the loads can only buy from the market maker. So Green matched with the market maker right away, and then it looks like VUCA and OLI were a bit more competitive, so they gradually raised their prices and they matched at the end of the market slot. So I'm looking to see if that pattern holds for the majority of the market slots.
Really cool. You see here also on the screen where these gray bar at the bottom is the external trades. And you see that as the PV starts coming in during the day, you have this kaleidoscope effect of trading with different houses that are providing energy. And once this runs for a few days, that it starts looking pretty cool. One other thing I saw was, let's look at the OLI storage 11. And it looks like the trading here is happening at a really low price, so like 20 cents, 19 cents, but they seem to be kind of selling within that range pretty quickly. So they're not buying a ton of energy, but when they do buy, it's at a very low price. Whereas green storage, for example, has a little bit, is willing to pay a little bit more for energy, so they went up much more quickly, and then they started to sell when the PV went down. What I'd be curious about is there a way to make the strategy so that instead of selling when the PV starts going down, you sell at night when there's a peak, when it's very expensive energy from the market maker. So I'd be curious to see if in the following simulations you're able to adapt and shift that curve a little bit later, or if your agent will learn.
Good feedback. Thank you, Olin. That's interesting to see. I actually expect that you would need a forecast that is multi-step in order to do that, but we need to think about that.
Cool.
You know, looking at this collaboration here and kind of joint learning or analyzing this, it reminds me of a conversation that I just had recently. A few days ago, it was with the CEO of a large engineering house. So they run simulations for whole countries, how prices could develop in the future, or how kind of you know, projections. What plans, what would make sense for the country to, you know, like a central planning. And we have been wondering, how could this tool be used to simulate the development in a country. Now, if I look at this collaboration right here, right now, imagine we would create a virtual digital twin of a country and then enable parties to optimize individually different agents. That could be, it essentially would be a crowdsourced optimization or simulation of an optimization of a country-wide development. That would be unbelievable, right?
Looks like the Miro board is getting pretty busy with people posting a lot of results there already. So that's cool to see.
Yeah, great.
I did one example on the Miro board where we have the base for experiment one that we already ran, and it's called template baseline. So I compared the two side by side for the zip code area, and the profiles look similar, but it looks like in experiment one already, we've somehow managed to reduce the peak in day one. So you can see where the peak was in the baseline and then where it is in experiment one. And I actually should turn on the peak analysis to show this. I didn't do that, but I just added that picture to the Miro board. Okay, I think I'm sharing my screen now. Okay, so here we have experiment one, and then I'm comparing it to the template baseline. And what I was looking at so far was the zip code market, because this is where we see community A, B, and the external trades. And then let's see. So the one on the right is the template strategies. Okay, cool. Yeah, so I mean, this is the first day, and what I could see is, this peak is at 13, and this one is at 15. So we saw some reduction in the peak here. And I actually I put the peak values for the entire week in the peak analysis function. So I think Colin already clicked on this earlier, but let's see. So here we can see the blue line at the top is the baseline. So we're still not quite at the baseline level yet, and we need to wait for the whole week to run to see if we reach or surpass this baseline.
Can you run peak analysis on the other one too? Or is that?
So it was these pictures. Can you see?
Yep.
And so on the left side, we have the running simulation that we have, and with all the smart agents of the teams. And on the right side, we have the template agents. That was with the ramp-up strategy. And so we see that we are analyzing here the average price of the second community, the community that only has normal houses with loads only. And so if the agents are smart, we see that they are trading less energy to the normal community. So when there is not enough PV or so on, they prefer to consume locally and store it inside the community A instead of selling to the community B. And therefore, in this case, the community B has a slightly higher average price because it has to be supplied more by the market maker.
Super cool. So this means that the community B, which is a totally dumb community, is receiving benefit from the community trading more intelligently. Is that right?
Okay.
Chris, sorry, I messed that up. You said the exact opposite of what I just said, right?
Yes. So we see that the community with smart agents, the team prefer to increase the self-sufficiency and self-consumption inside the community A rather than directly selling to the community B. But we are still seeing that the community B can benefit from a smart community next to it by the average price.
So the smart.
I guess maybe we also don't know for sure, because if OLI wasn't trading, then they didn't have excess PV that they could have sold to community B, for example. So maybe that is another factor that we have to take into account. But it's cool to just see in this graph that whenever the line drops below 30 cents, that's when we know that community B is getting a benefit from having local trading.
So this is pretty cool. It's changing live, but this is a dumb storage, or template strategy storage, and it's at minus 39 cents right now. It's total profit. And green storage, it's currently buying up again, but it's at minus 1.2. So it's at like a 3 or 4x benefit when you have the intelligent strategy versus the template strategy, which is really
wow. That's really interesting.
We'll see how it all settles out at the end. But
yeah.
Which team is that?
It's Greenlytics.
Yeah, we didn't really show the scoreboard yet, but we could go to the scoreboard and just look at all the storages at the end of the simulation and then see if there was if there was more profit from the teams versus the template strategies.
Cool.
Let's do it at the end.
Sounds good. But it is cool. You can see that there's, at the beginning here, when they're ramping up, the storage is ramping up, you have really low prices. You're getting 19, 20 cents, 15 cents even, which is super low. And then when they're selling, they get pretty competitive rates at 26 cents per kilowatt hour. So really well done on the storage strategy there. And we'll compare what the template strategy is getting 19 or 20 cents, and then they're only selling at 22 cents or so. So that's why there's such a difference. Really good job.
Yeah. Now imagine, I mean, this is exactly. No, think a step further, and you're kind of a vendor or provide an app for the final consumer through this degrees of freedom. I mean, you could, you could enable final consumer to predict the income of any flexibility before they buy it. Yeah. And that is enormously interesting.
Can we ask the teams what exactly their storage strategy was, or will they share that more at the end of the challenge?
So that'll be that's challenge question 1, or experiment like challenge question 1. So that'll be what they'll present on a little bit at the debrief.
Okay.
I think for now it's not too sensitive anyways, because I mean the only variable right now is to hit the right price. We have like 4 or 5 more variables coming into the game later, which is way more challenging. Yeah.
Yeah, I'm excited to see what people come up with, and then I'm more excited for challenge question 2, which lets you be a little bit think maniacally. Some of these charts really start looking beautiful though, with the dots all around with the buys and sells. The load, for example, buying seems to have this really cool pattern where it drops really quickly, buys at a super low price during the day when the PV is selling to it, then goes all the way up. Cool patterns. And OLI, your storage looks like it's trading again pretty well, so that's great. Got some low prices too.
Same hierarchy as the...
Interesting, now we have a PV day that just happened at a very low PV relative to the other days for the most part. So we'll be curious to go through the results and see how that compares to some of the other days.
Wait a second, what is this? This was from the data that you put in there for the...
Yeah.
You did this on purpose, or?
Yeah, we have a variation in the solar profile for the day. So we have some days with very high generation compared to load, and other ones with very low.
Mm-hmm.
This is exact dates from the EVS case. So I think it's March 8th through 14th, 2014.
Mm.
So it's according to them, like their measured data.
Mm-hmm.
Yeah, so it's interesting here. You see that the price here on the very high production day for green PV5, for example, is really low. So you get down to basically the feed-in tariff price because you have an overproduction.
Mm.
On the other days with medium generation, you have some price in the middle, a couple drops. But on this low day, it's much higher. You're paying a premium for that solar generation.
Mm.
So it looks like we may need to think about a way, because this green battery has done really, really well, but it's going to end at midnight, likely with some energy stored in it, which is valuable, right? So it's valuable to sell. So maybe that we can find a way to say like potential of energy stored or something like that, because it's a good thing to have energy still there at the middle of the night and sell early in the morning, because that looks like great. Looks like you've already adapted it, which is really cool too, based on that initial feedback. Finished. Okay, simulation's over. Great job, fantastic. So let's give a 6-minute break, and then we can dive into the debrief. And in the meantime, just kind of click around, see what you see. So it looks like the storage wasn't able to actually get rid of its energy, but it still ended up in the negative, and it has 9 kilowatt hours to be able to sell, which is great. Let's see if the other storage is. Looks like OLI was able to sell theirs all the way. Same with VUCA. No worries at all. So let's get started with the debrief. Stefan, you're here too?
Hello?
Hello?
I'm here, Colin. Hi.
Okay, great. Debrief. So, Jan, if you don't mind muting for now. Thanks. Okay, so first of all, great. So exciting that experiment 1 finished. We had a couple things go wrong along the way, but I think we've sorted out most of those issues with the agent strategies. But just in terms of results, there's a lot of interesting things that happened. I think we'll need more data points for sure to say that in this market design, you can definitely reduce the peaks with intelligent agents, for example. But let's go through some of the interesting results. All right, okay, great. Peak reduced compared to baseline with all agents trading. Oh, you can click on it, this is great. So we set up a baseline here where it was just the template trading strategies. And we wanted to understand, is the peaks where you're buying from the market maker and selling to the feed-in tariff, can you change that just based on more intelligent battery trading strategies? Because the battery trading is all that would affect that here. And so what it looks like is that this is the only day that we had all agent battery, like all the batteries trading at the same time, all teams trading at the same time. And this is the highest peak for the PVs. And it looks like the total peak, if we go into the results, was, let's see, about 3 kilowatt hours less than the baseline peak export. So it's from 23 kilowatt hours down to 20 kilowatt hours.
And right now, I mean, we don't have grid fees set up to do that, but it's probably helpful for them to see how the financial incentives that maybe they're seeing impact the behavior on the grid.
Absolutely, which, yeah, I haven't thought about it, which means, you know, now as a next step, you know, once we enable the grid API and they rise the prices there, this would have impact to every trader. Yeah, so meaning at the end, the system basically also indirectly forces the trading agents to foresee a peak, because to foresee a higher price with this. Yeah.
Yeah, this whole thing is about aligning incentives. So if you're seeing one metric that somebody cares about, the energy traders, which is reduced energy bill or revenue, and you see a totally different metric that seems uncorrelated, which is the peak export and import, and are able to make those align in terms of the gain to both parties, that's when you start having real benefit to the grid.
Okay.
All right, next one. PV prices are correlated to the amount of generation. This one was super cool. So here on the highest day of PV, you see that the energy price here, which is down here, goes all the way down to the feed-in tariff and kind of hovers around that area. When there's a day of medium generation, the prices sometimes go down low, but for the most part stay in this kind of middle range. And then when there's low generation, the prices stay very high. So you see the market in action here, which is really cool. I'm sure we could see something similar on the loads and storages as well, which could be interesting. Okay, so this one's the one that Chris put together. Do you want to quickly go over that again, Chris?
Yeah, sure. So we said that we have two communities inside this setup. And so we have the smart community with all the smart agents and generation and storage, which is the community A. And we have another community, the community B, which is only a consumer community. And so there we are looking at the average price of the community B that is only consuming energy. And on the right side, we have the template simulation, where we have template agents. And on the left side, we have smart agents. And so with the templates agents on the right side, we see that in some cases during the first day and the second day of March, the community A is selling energy to the second community, community B. And therefore, instead of buying from the market maker, the community B is able to buy at a smaller price. And with smart agents, they had a different strategy, which was to self-consume more locally, so in the community A, which means that less energy was exported to the community B, and therefore the community B has a slightly higher average price than before.
To my opinion, this is an enormously strong message, because right now, most of the community efforts, community energy efforts, are just looking at one community. And so they're making the community more intelligent, you know, because you need data to be able to trade between each other. But through such a scalable kind of market design, where you place the grid exchanges according to grid topography and enable actually intercommunity trading, the interesting thing is that actually those standard load profiles can benefit a lot by being connected to the intelligent communities. And that is, to be honest, I haven't seen much research in this specific field. Usually it's just this one community and what's the benefit of trading between them, but not in the expansion of the peer-to-peer trading to broader scale. Yeah.
Mm. Great.
But in this case, it shows that the non-equipped community get it worse, because the smart community trades better for itself. So it's an incentive to get equipped and become smart, because if you don't, you are going to be worse of it.
Well, I would say this goes into both directions at the end, because so I mean the major difference is if there is an agent which is even trading upon a standard load profile, the agent can choose different type of suppliers, and so that's already a huge difference to just having one supplier. And so there is an efficiency increase here, but on the other side, I fully agree. If you can translate all these degrees of freedom from through this API to the final consumer, then you basically can tell the story to the final consumer that the more intelligent you get, the better you're off. Which basically puts the agent, the final consumer into the same situation as every trader. The more flexible my capacity, the better my revenues, right? Yeah. But I wouldn't necessarily say like, hey, all the guys around you get incredibly smart and therefore you lose. I mean, I would maybe say you lose on opportunity cost. But if there is a market maker at 30 cents and everyone gets the 30 cents right now, well, I mean, yeah.
All right. So here, the storage is buying as the PV ramps up and selling as it ramps down. So I asked it, could it learn to buy at the peak and sell at night when there's zero additional generation for green storage? And I'm pretty sure that green storage actually adapted halfway through the simulation, because if you look at their profile, which is, if you look at my screen sharing now, these first 3 days, they trade pretty quickly where they get rid of the energy. And at the end here, they wait until later in the night to start selling their energy all the way down. Unfortunately, what that meant is that at the very last day, and this is a day of very low PV, so you see kind of how their storage suffers there. But this very last day, they would have a much lower energy bill overall if they were able to sell this excess PV down to zero. So maybe we can try and account for that in our scoreboard results, but based on how much energy is left in the storage.
Yeah, maybe just 5 minutes before end the simulation, we scream into the room, bank run, sell everything you have, so that then.
But now we'll jump into the challenge question. So we'll just have each team go through and start a conversation about how they approach their agent. It looks like we have a couple strategies posted in the free space here, which is great. So let's go right into it. Vuka, why don't you go first?
So we have the information about our energy requirement and available energy for every 15 minutes. And starting from that, we can say, are we a net importer or a net exporter? So if you're an importer, we go to the yes, to the first strategy for pricing. We are starting from the lowest bid to the highest bid linearly. And we know that in the end, we have to buy the amount of, we have to sell the amount of energy. Buy the amount of energy at the maximum price. So we want to, in the end, get all our energy requirement in place. We buy it at 30. So if you're an exporter, then we have another question: shall we export it, or shall we charge our batteries? So we are making this yes and no decision, and doing actually the same pricing strategy as it was on the net importer case. We are this time decreasing the offers and finalizing it at a market maker price of 30.
So, Oli, if you're on, would you like to present yours?
Yeah,
Talk
sure.
through.
Sorry, we had some troubles with our code, and that's why we didn't have the time to write up something. But I can definitely explain what we were planning to do. Since we also didn't have a lot of time to prepare a prediction model, we created more using a certain number of states to make a decision tree, basically, and use weights to assign what should be done. So, and the states that we were considering are to look into how much, first of all, how much the PV is available in our PV is available. Then to look into what was happening in the last 6 time slots, to look at the trend for the energy trading as well as for the market price, average market price. And lastly, and how also to time of the day. Sorry, yeah, time of the day to know where exactly we are during the day and to have some ideas based on that. So we use these parameters and we assign certain weights to further divide it into certain parts and then assign weights to it and to then decide what should be done with from the base case. That was basically our strategy.
All right, now Greenlytics.
Yes, we're here. Okay, so I will present the first part with the prediction step, and then Elias will present more on the strategy when it comes to the decision. So when it comes to the prediction step, so predicting the market prices, we decided to go for a fairly simple but adaptive autoregressive algorithm. So it takes in 4 or 3 parameters. The last observed prices, and the sum of all the PV that we have in our under our governance, and also the sum of the load. So those are the factors that go into the forecast. And this is done with this kind of, very simple, just a linear model that takes a parameter matrix B, and then it takes the features from X, and then it makes the forecast for the next step. So we have then 3 parameters or 3 coefficients that we need to learn. And the reason why I went for this is because we have the historical data, but by training on the historical data, we don't have the environment where we trade it on, because we're not trading with smart agents. So we wanted something that was adaptive for sure. And also there was not that much data. So we wanted to have a model that is not over parameterized, so that it can actually learn something from the available data. And lastly, that we can set a reasonable prior on the model. So actually we do not train our model before we start the simulation. We actually start training it when we start simulation. And the prior that we set in the beginning of the simulation is that we assume that we predict only the persistence forecast, which means that we take the last market prices and predict those for the next step. Okay. And then as we get new data points, we will update these coefficients and we will do something slightly more sophisticated. When we investigated, or when we looked into these coefficients, we actually got something like, 0.9 for the last price. We got like minus, 0.36 for the PV. So that means that the price goes down when the PV is high. And then we got, I think, 0.15 for the load, which means that the price goes up when the load is high. So those parameters made sense also with the setup that we had. And yeah, I just added, so yeah, this last in this equation, that the update equation, I don't know if it's not that important, but you can see this small, this lambda that is in there, and that's a forgetting factor. So we learn the algorithm, but we take more into account the latest observations. So we forget every time we forget some of the historical data. I think that factor was like 90.99. So we exponentially forget the historical data and we trust more the recent data because we know that it's adaptive, or like, the environment is changing. So we should have a forecast that's changing as well. Okay, some problems with the forecast was that in the beginning, especially when you had all the prices, that was 30. Then, of course, the default state is that it will forecast 30 for all the prices because it's just taking the last value. So we happen to have that a lot, and that had some implications on our decision step, which Elias can tell more about. So we're planning to update that.
Yes. Regarding our decision, can you please, Colin, focus on the figure below, which is now half shown? Yeah, I can start with that. So basically, we thought we can start with a simple approach, basically expanding the dump agent approach, where the price is increasing at its tick for the load and decreasing for the PV. And so we're wondering if we change this linear increase or decrease, what will be the best option, which, let's say, the best function to do this this move from the first to the last tick. And so if you focus on the figure below, the one, so we thought about exponential, logarithmic, but then we decided to go to a sigmoid function, and which is the blue one for the load. So we start at the first tick at the very low price, almost close to the feed-in tariff, and then we gradually increasing up to the grid fee. The opposite is for the PV production. We start almost from the grid fee, and we're decreasing down to the feed-in tariff. And regarding the storage, for selling, of course, we start with a very high price, which is higher than the PV. We decrease at some point where we meet the load curve. And in that point, we assume that we self-balance the load at the same house. So if the load hasn't been sold till that point, then it will be covered from the energy in the storage, if there is any.
Cool. Great. So really great job with experiment 1 and the challenge question. Really cool to see how different the strategies can be, but how the trading still occurred, and there's benefit that we showed in some of the results already. So we will crunch some of those numbers too, and you might see some of those results tomorrow. We'll show you, or on Saturday. But for now, let's go right and dive right into experiment 2, unless there's anything else we need to go over.